Hey guys, my name is Manish Yadav and it's my second video for EMAC 303 for extra credits. Today I'm gonna do second order linear elliptic partial equations. So this is our equation d2 d square t by dx square plus d square t by dy square is equals to 0. So this is our change in temperature in x direction and change in change in temperature in y direction. So let's take an example that I have a rectangular plate with the boundary conditions like T is equals to 300 on top side and 100 on right side, 75 on left side, 50 on the bottom side. So to solve, and we just need to know the T at inside. So this might be a function, this is a function of x and y. To find this function, we just need to discretize our equation. So let's discretize it. So d square t by dx square, which is our change in temperature in x direction. So t I minus 1 j minus 2 ti j plus 2t plus t I minus 1 I plus 1 j by delta x square means change in x cos square. Okay, and for y, d square t by dy square, which is ti minus t I j minus 1 minus 2 ti j plus t ti j plus 1 by change in y square. Okay, so plug these discretized equations in our PDE. So just put it ti minus 1 j minus 2 ti j plus ti plus 1 j by x square plus ti minus ti j minus 1 2 ti j and plus ti j plus 1 by y squared is equals to 0. So delta x and delta y is 0. That's mean it's need to have a square because our x and y direction is equal. So just make it a little simple. So I just simplified this equation and what I found is like ti minus 1 j plus 2 ti I plus 1 j plus t, or not here 2, it's just like t, sorry, and tij plus 1 plus tij minus 1 minus 4 tij. This is our actual function. So here the x and y got cancelled out and this is our actual function. So when takes an example, like we are taking I and j, right, 2 and 3, take it I as 2 and j is equals to 3. So take it, so our 2 and 3 is this point. So our ti minus 1 and j will be this point because we are moving along to x direction and we are just doing 1 minus in our x direction. So this temperature will be at this point and this will be at this point. So these are our change in y direction. So this temperature will be at this point and this is our actual function, which is it's a okay. So let's make a grade to solve this example. So just take a large grid is equal. Okay, so this will be our m, this will be our b, and this is n. Okay, so t at 1 1, t at 1 2, t at 1 3, t at 1 4, t at 2 1, 2 2, 2 3, 2 4, 3 1, 3 2, 3 3, 3 4, 4 1, 4 2, 4344. Okay, so at our t1, our t will be, so we know our boundary conditions that I told you, like I have t 300 at the top, 100 at the bottom, and 50, sorry, 100 at the right side, 50 at the bottom, 70 at the left side. So our t11 will be this point. So this is our, this is half of 75, so and plus 50, so it's 125, and it's half of this, which means 125 and 62.5. So let's take it 62.5, and this will be our 1. Rest of the things are 0. At t12 or t12, this point is our 50, t13 is our 50. So let's do it. 0 1 0 0 0, 2 zeros and 1 0 0 0 0, and this point will be our, so t at 1 2 will be our 50, and this will be our 50. Okay, at t4, this is our, also this is also our outline and a boundary condition, so we know this will be exactly half of these two, so it's 75. At t4 it's 75, and take it 0, rest of the things will be 0. Okay, so 2 1 is our 75, and 1 2 3 1 0 0 0. Now this is our interior point t2. So to solve this point, we need to use this equations. So let's put 2 as I and 2 as j. So we are trying to solve this, and what we'll get is t1 2 plus t32 plus 3 2 3 plus, oh sorry, that will be like 2 1 and 2 3 minus 4 t 2 2. So this is our diagonal. Okay, so let's take at 4 2 2. So this is our diagonal, and our t12, we have t12, so this will be the second, which is our 1, and t13 will be our 0, t1 will be our 14 will be 0, t12 will be 0. Then we have 3 2, which is sorry, we have 2 1 also, so 2 1 is, yeah, this point is also 1, and we have 2 3, which is the next to this, and we have 3 2. So this is 1 2 3 4 5 point. So 1 2 3, sorry, this is the fourth one. So 1 2 3 4 and 1 2 3 4. Rest of the points are 0. So this will go similar for the whole equation, and we can solve it. Now we'll do our MATLAB code for this problem. Now we are gonna do our MATLAB codes. So but I'm not good in typing, so I already done my codes, and now I'm gonna tell you what is it and how does it work. So I just start from like my differential equation. So as I told you that I have a diagonal is -4, so I just need to represent my diagonal is -4, and this is okay. So and this is like changing x and changing y direction by the like every one step. So these are the number of grid points, and is like how many grid points we want. So I just put like nx is like 40 grid points in the x side and 40 in the y side. And our grid is like x will be our start from 0 0 to 1 point is lx, and to the nx like to the 40th point, and same as in the y direction. So to build a B matrices, so our A matrices will be like zeros and n rows and n column. For our B matrices, we just need n rows, just one column. So for the loop over interior points, so this is like our first interior point is like 2i, starts from 2i to j2. So I just from, and after that it's like 3 2 2 3 and all of them. So I just took I is equals to 2 nx minus 1. So nx is our last grid point is 40, and our inside point will be like minus 1, and same as y direction. So n is our I j minus 1 into nx, which is row, and for for a point is our diagonal, and for like our left side of our diagonal and right side of our diagonal will be 0, because these points are interior points, and I won't take anything in the right side for the function, that's why it's 0. Otherwise it will be the this will be the value of the function. And here this is the top and bottom side of the function. So this is because it's also from the interior points, just because of that I haven't took anything on the right side. This is our B matrices, and at like n is our interior points, that's why it's 0. So I have put my boundary conditions here. So my left boundary condition is 75. So for I1 is our 70, like at the I1, so ji is ny, which is our j start at 1 in the y direction. And I put my boundary conditions for right side, then it's mostly similar to the left side. Then I put my boundary condition for the bottom, which is like j is equal to 1 for the, and for I it's 1 nx in 1 till nx is our the grid points in x direction. So our n, the value of n will be like 1 plus j minus 1, which is our j minus 1 is our like 1 point less from the ny, which is our 40 grids point in y direction into an x. So our A matrices will be like ANN, which is our first point in for the bottom condition, and the bottom condition is 50, like the maximum temperature will be 50 on the bottom side, and it's almost similar to the top side. So for solving this temperature, we just need to divide the matrices A and B. So convert vector of temperature into Tij. T is our zeros, nx and ny. This is our temperature, and we are doing this example in terms of temperature. So our I is like 1 till nx, which is our grid points, and j is 1 2 and y, and our function is n I plus 1, sorry, I plus j I minus 1, like x direction, and y goes to 1 minus our grid points into an x, like into the x direction. Tij is equals to tv by n, and here our loop is ended. So I just put put the plot to the solutions, and figure 1 and figure 2 is like suffix with xyt and x label for the x and y label for the y. And now I'm gonna run this code, and this is what I get. And this is like, so here in this direction it's 75, and here it's on 50, and this is our top side which is 300 degree, and this is our 100. So this side is our 100, this which is our, I think, yeah, that's our right side. This is our bottom side, and this is our left side, and this is our top side. Thank you.